Making complex decisions. Sequential decision problems. A sequential decision problem is a problem in which the agent's utility depends on a sequence of decisions. Suppose we have an agent situated in a 4 by 3 area with given moves up, left, right, and down. In a deterministic environment, with a move up, up, right, 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 the agent will get into a terminal state. Unfortunately, the environment won't always go along with this solution because the actions are unreliable. Here's a model of the stochastic motion. Each action achieves the intended effect with a zero point 0.8 probability. But we could say that an action is slippery and there's a 0.1 probability the action moves the agent at the right angle of the intended direction, or it bumps into a wall and stays on the same position. For example, we have the agent in 1, 1. We chose the action up. With a probability of 0 0.8, the agent will move to 1, 2. With 0 0.1, it can go right to 2, 1, and another 0 0.1 probability of bumping the wall and staying in 1, 1. With that, with 0 0.8 probability for each action, we can reach the terminal state with probability 0.32768. But there's also a chance to reach it by going the other way around, having probability of 0.32776. A transition model is the specification of the outcome probabilities for each action in each possible state. It is denoted by TSAS prime. Reward. For example, we are given a negative 0.04 reward for each non-terminal state, and an agent reached the terminal state with the reward plus 1 within 10 steps. The total utility will be 0.6. Just do the math for that. Markov Decision Process, or MDP. An MDP is the specification of a sequential decision problem for a fully observable environment with a Markovian transition model and additive rewards. It is defined by the following: an initial state as 0, transition model TSAS prime, and a reward function RS. So we now know what an MDP is. The next question is, what does a solution to the problem look like? We have seen that any fixed action sequence won't solve the problem, since the agent might end up in a state other than the goal. Therefore, a solution must specify what the agent should do for any state that the agent might reach. A policy. Pi S denotes the action recommended by policy, pi for state S. Every execution of a policy, the stochastic nature of the environment will lead to a different environment history. The quality of a policy is therefore measured by the expected utility of the possible environment history generated by that policy. So if the agent has a complete policy, then no matter what the outcome of any action, the agent will always know what to do next. An optimal policy is a policy that yields the highest expected utility. It is denoted by pi star. The balance of risk and reward changes depends on the value of Rs for the non-terminal state. So how's that? For example, we have this world and a time that is equal to 3. Each step is equal to a second. Under the time pressure, you can take action B, head straight to S3 and get the reward of 5. Or you can take a 2-step action A, head for S2, and get a 10. So that's it. Risks and rewards. Optimality in sequential decision problems. The first thing that we need to know is if it is a finite horizon or an infinite horizon. Finite horizon means that there is a fixed time end before the game is over, having a non-stationary optimal policy. Infinite horizon, with no fixed time limit, on the other hand, there is no reason to behave differently in the same state at different times, hence a stationary optimal policy. There are two types or two ways to compute the utility of states. But how do we calculate the utility of state sequences? We need a stationary policy. Stationarity means that if two state sequences S0, S1, S2 and S0 prime, S1 prime, S2 prime begin with the same state, example S0 equals S0 prime, then the two sequences should be preference ordered the same way as the sequences S1, S2, so on, and S1 prime, S2 prime, so on. Here's the two way to calculate the utilities. First is the additive reward, where the utility history of the states is equal to the reward of state 0 plus the reward of state 1 plus the reward of state 2, so on. The second way is the discounted reward, where the utility history of the states is equal to the reward of S0 plus the gamma times the reward of S1 plus gamma raised to 2 times the reward of S2, and so on. The gamma here is a discount factor, a value between 0 and 1. Value iteration. Value iteration is an algorithm for calculating an optimal policy. The main concept here is to calculate the utility of each state and then use the state utilities to select an optimal action in each state. We use here the Bellman equation, where the utility of a state is equal to the reward for a state plus the discount factor times the possible actions and the expected utility for the action. Given this 4 by 3 dimension and a gamma of 1, the discount factor is given. We will use the Bellman equation and we will get this. The reward, the gamma which is 1 discount factor, and the possible actions with the utilities of each action. Computing that, we will have these values. And based on these numbers, we now know that the best action will be going up. In this pseudocode, first we create a loop to go to each state, then perform the Bellman equation. Then we store the difference of the new utility to the original utility until it becomes less than the termination condition here, which is the expected error. Then it returns the utility. That's how you do a value iteration. Policy iteration. We use policy evaluation, where one can evaluate how well a certain policy does by computing the value function induced by that policy. In this pseudocode, assuming we have a policy pi, we will take that action for the state and calculate the utility of the next states with that policy. We'll just continue that if the utility does not seem to change. That's how we do policy iteration. Okay, so for example, we are given this policy and this formula. We use this for the policy iteration. We compute the utility for using this policy for the first state. And because the policy iteration uses the policy, then compute for the utility of that policy for the next states based on the first state, we will also do that for the second state. And we will compute for the utility until the utility changes. Partially observable MDPs. Partially observable MDPs or POMDPs is a problem where the agent does not know which state it is in, so it cannot execute the action pi-s recommended for that state. The utility of a state S and the optimal action in S depend not just on S but also on how much the agent knows when it is in S. POMDPs are defined by the following: a transition function, reward function, just same for the MDPs, an observation model OSO, and a belief state B. Suppose we have a belief state S, and we take some action A. We will use this for having a new belief state, B prime. Simply put, we have a B prime equals forward BAO, where the next state will be stored on the observation model. So here's a decision cycle of a POMDP agent. 1. Given the current belief state B, execute the action A equals pi star B. So it's just like the MDP, only that the states are not really complete. We only have belief states since our agent does not really know where it is. Number 2, receive observation O. So we will put that in the observation model. Number 3, set the current belief state to forward BAO and repeat. Just that. So it can be shown that an optimal policy for an MDP is also an optimal policy for the POMDP. In other words, solving a POMDP on a physical state space can be reduced to solving an MDP on the corresponding belief state. Though the details of the algorithm is beyond the scope of the book, so that ends our discussion about POMDPs. Thank you.